Hello everybody and welcome to this third part of wing motion simulation using OpenFoam. In the first part we presented the snappyHexMesh, how to mesh our domain, the wing within a square. And then in the second part we've seen the simulation in steady state using SimpleFoam. Then in this part we will see how to process the wing motion using PimpleFoam using a dynamic mesh. So let's start. So here is our folder wing motion 2D PimpleFoam. We will start at first by copying the mesh because we don't have yet the mesh here. We will copy it from SimpleFoam constant. So I'll do it using the terminal. I'll open terminal here, then I will copy the mesh from the wing motion to the SimpleFoam constant polymesh into here constant, so we can check. Yes, we have our mesh, it's already here. So for now what we want to do is to map fields. You can check this video. I'll interpolating results between meshes using map fields. This is of Joseph Nagy. You can find more information about this tool. It's a very useful tool. I will leave the link of this video in the description box of the third part. Then I will let you know how to use this tool. So for the map field, for example, here we have already the results of the steady state simulation. We have the converged results in the latest time. So here we have converged simulation. Now what we want to do is to start our unsteady simulation from this as the start time. So we will take the velocity, for example, instead of taking this file, the U, and initialize it and start from the beginning, we will take the computed results of velocity and all the other parameters of turbulence and pressure from the latest time. So it's calculated already in steady state. So we will take these results and copy them in the PimpleFoam. So for this we just need to go and execute the map fields tool. So what we need to do is to run map fields. Then from which folder we will go and precise its 2 points. So it's the previous folder, wing motion from SimpleFoam. Then for the source time, which folder it's gonna take the results, so it's the last folder. We will do source time, latest time. For the mesh, we have consistent mesh between the two cases. You can, because this tool of map fields, you can also use it when you have the same geometry and different meshes. We have, for example, coarse mesh and refined mesh. It does the interpolation and gives you the variables to compute. This is why we need to precise here that we have consistent mesh, so we have the same mesh. It just will take the values from the same nodes and implement it in the nodes of our new simulation. So we will mention consistent here. So now it's done. We can go and check here. So here we have our variables we can check if we open the velocity file. Perhaps it will take a while, but yes, it's in a binary format. So we can see the values here because it's in a binary format. Anyway, it's copied from this folder of 3000, the latest time of SimpleFoam. It's considered as the initial condition of PimpleFoam in order to avoid to restart the simulation from the beginning. So this is the idea of the map fields. Then here we have a new parameter, which is the point displacement. It calculates in fact the displacement of the wing, because we will treat the motion of the wing in the mesh, so it will take into consideration the displacement of the wing. So what we need to do is to copy this file and paste it here in the initial condition. So now we are done with the 0 folder. Let's now go and see the parameters of our dynamic mesh. So this is the dynamic mesh dict. It's in the constant folder, and here we are precising the solver, which type, then the libraries that we should include. Here also the solver, the motion solver, which one, then the patches. Here the inner and the outer distance. In order to get for the inner distance, it's the extent of the solid body motion region and body. Then the outer distance, it's the let's say it's the zone around the wing where the mesh is morphing. Then here we are precising the mass, the center of mass, the moment of inertia, and all the parameters relative to the wing. Then here we have the gravity, the rho of the fluid, which is air. Here also we have solver. Then we have the constraint here. This this part considers the motion of the wing. The first one, it's Y line. It considers the linear motion of the wing. Then the Z-axis, it considers the rotational effect of the wing in the domain. Then here the restraint, it specifies the it takes into account the forces applied on vertical and axial. So it's more like here it's focused on body rotational motion, and here it's vertical, so it's in the linear motion of the wing. Here for example the stiffness, it's the proportional to body displacement, dampen to velocity, and so on. You can find more details about the parameters mentioned in this file in this link, parameters definition dynamic motion solver FV mesh. I will mention the link of this web page in the box description, so you can read more about more details, and also if you want to for example change the parameters or adapt it to your case. So here we have the mesh. For the transport properties, it's kept as for SimpleFoam, it's the same. Turbulence properties as well. Then in the system we have the usual files, FV schemes, FV solutions, and control dict. Here we specify the start time, the end time, then write-in control, Then here the function object to relative to the body, to the wing, to calculate the angle. And here we have the solver. Here we have the solver, PimpleFoam, the start time, and all the other parameters, the usual parameters of the control dict. Then here we have a file of the decomposition of the domain, because PimpleFoam is based on NCD. It will do NCD simulation, so it will take a while to finish. So in order to accelerate the treatment, the simulation, it's better to run it on four processors, or 8 or 16, depending on the capacity of your laptop or your cluster. So here we are specifying the number of decomposition, the number of subdomains. We have 4. Then the method of decomposition, it's simple. So simple, we are devising the x-axis on 2 and the y-axis on 2, and we are keeping the z-axis as it is. So 2 times 2, it will give 4. So these are the simple coefficients. For this we can just remove it, since we are not choosing here the method hierarchical method, we are choosing the simple one. So let's now go and execute the decomposition of the domain. So decompose bar, and here we have our domain decomposed on 4 processors. Then now we can go and launch our simulation using the command, the parallel command, so which is run np number of processor 4, then parallel, then we have the solver PimpleFoam, and it will be written in log file PimpleFoam. So here perhaps I need to make the solver at first, PimpleFoam, then parallel here, then the log file. So let's check here. So it's okay. So now we have the log file here, and the simulation, it's already run here. Just a new terminal. In order to check the log file, we can just type tail f log, and we have here the evolution of the simulation here. It will take a while because we have it will run until 5. With this delta t, I imagine that it will take a time. So now it's done. We have the end time equal to 5. Let's check ls. So we have our results stored in 4 processors folders. So now we need to reconstruct our results. Reconstruct bar. So it's done for results reconstruction. We can check this. We have all our folders. So here we have folders until 5 and time 5. So let's now run PimpleFoam to visualize the results. So apply. Here is our wing in the domain. Let's choose U and change color. Then we can run over the time. We can annotate time as well. Filter, search, annotate time, apply, and apply. So here we can see that when applying a pressure on this wing, it starts moving down and up, and it gives this shape of the flow. The air is introduced from this boundary, then apply pressure on the wing, then the flow, when hitting the wing, it starts getting this shape. I'll just stop it and go to the last time step. We can do as well the not contours but streamlines, stream tracer. On a point source. And make the radius equal to 2. Apply, and the number of points, I make it. Then I reduce the opacity here to 0.2, and I'll do it like this. Then I choose a glyph, a row to the glyph, then I choose only 100. Then here we have the sense of the flow. Here these vectors reflect the movement of the wing, because when it is moving down, it involves flow down here. So if we choose scale it using U, it's too big, so let's keep it without any scale, and increasing the number of samples. It's too much. It's okay now, it's okay. Or 300s. Okay. Then we can move it so we can see the movement of the vectors over streamlines, and also the movement of this wing during the flow. So I stop it here and go into the last one. You can as well save your animation by going here, save animation, save it in Postprocessing, or call it A, and OK. For the background, I'll choose weight background. Then for the frame rate, I'll choose 5. It will record one frame and skip 4 frames, so it will be faster. It will take a while. So it's done for the animation. Let's go and check the result. So it's here. We're gonna open it and we will see the movement of the vectors and the variation here, movement of the wing up and down. This is not very clear because of the color. You can just go and modify these colors from here, or you can also increase the opacity, this solid color, and you will get a clearer visualization of your streamlines and vectors. So this is all for the wing motion simulation using PimpleFoam. Thank you for watching and see you in next video.